Hi, this is continuation for Power Electronics module, and today we have a lab, and that lab is about buck converter simulation. I will use LTSpice to implement simulation for buck converter. I will build from scratch a buck converter with all components and select some diodes and also Mosfets and show you the waveforms of each component. I will go briefly about every part here because you have to duplicate the work and also to validate that you understand every bit. So task number 1 is to build the converter and to show you the waveforms. Task 2 is to show you the impact of the capacitor parasitic component like the ESR and ESL on the output waveform, because we have covered in the lecture how the ESR, the series resistance and series inductance for the capacitor, will impact the shape and the voltage ripple. Okay, so we will see that in simulation as well and see if that's correct or no. And then we will go through discussing the high side driving. We know in the buck converter that we have a Mosfet which is considered as high side Mosfet. So how we are going to drive it? Is it by just a Mosfet or sending PWM straight away to the gate, or there is some other configuration that we have to discuss? I think I covered that in the lecture, but today I'm going to implement the Bootstrap and also another topology to show you the what are the challenges to drive high side drive Mosfets and also what are the solutions. And then we are going to build on all of these. Now we have the buck converter and we have the high side driver. We are going to add a closed loop system. We will just implement a very simple system, okay, using a comparator, and to decide if the output is really what we want, and to change that controller. I will go through on-off control and then hysteresis control, and then we'll implement a simple P controller, and we'll leave for you the other advanced controller if you want to implement it. And I'm expecting from you to duplicate what I'm doing in each part here and understand it very well, because part of your coursework is to provide the design, a full design for buck converter with feedback system. So the validation, the theoretical validation for the design I'm implementing today is not available. So many of the steps here will go by the try and mistake and see how the output will be, and then we change some parameters. And this is the learning that I want to deliver to you. I don't want to give you a simple and ready circuit. I want you to make mistakes with me and then to see what other solutions to correct and finally provide a buck converter. So let's start now. So let's start with the first task. We are going to build a buck converter now. So let's go to the component and we choose the voltage supply, and then we want a Mosfet, and we go to the component again and we go to NMOS here, okay, and then select it and rotate it, Control R, and then another Control R, okay, because we want the source here to be on the right, and also we want an inductor. So let's rotate it like this, Control R, and then a diode, another Control R, and finally a capacitor, and we want a load like resistive load, okay, and we have to insert here a ground, another ground, another ground, another ground. We can connect all of them together, but let's do it like this. So you can follow me building that one like that, step by step. And now select the values for each. So let's start with the voltage source. We will assume it's 50 volt. And then we are going to look at the initial value for the inductor. Let's say 1 millihenry. For the capacitor, 100 microfarad. For the resistive load, say 100 ohm as initial value. Now let's select the Mosfet to be one of maybe the most popular ones, and let's go to IRF 1407. So here is IRF 1407 because it has a very low RDS on, and I like this. So let's go now to the diode and let's select it as one can handle maybe more than 5 ampere and can also handle more than 50 volts. So let's select one, and you can just press on the voltage tab or the current tab and to go to each group as you want to select one of them. So I will be selecting MBR 20100. So this seems alright for me, and we can make just some space on the left here just to make the driver. Okay, so this is the initial buck converter, and now we can really apply the PWM, and I will go for a simple PWM generator, which is the same as voltage source like this one. Okay, but as we know that we can just rotate it, as we know that the PWM I'm applying at the gate here, it should be between the gate and the source. So that's why I will make that voltage supply between that gate and the source, not the ground. Okay, because that MOSFET is high side MOSFET. So I have just to move this like this and like that. Okay, and then this is the source, which is the PWM source, which is applying the signal between the gate and the source, not the gate and the ground. So now let's select that one, right click and go to advanced and go to pulse, and we can select the PWM description. The initial value is 0, the V on value. This MOSFET can turn on 15 volt, 18 volt. So let's say 15 volt. The time delay, I don't want time delay. The rise time, say 1 nano, the fall time 1 nano, and the turn on. So if we want PWM 10 kilohertz and the duty cycle is 50%, that means I wanted 50 micro and 100 micro the period. So 10 kilohertz means 100 microsecond, and let's set completely on, and we can just move it like this and rotate it, and here it is. Okay, so I think our PWM is ready, and now we can run our buck converter, and we can run it like this, but we have to select the transient time, say 100 millisecond for example, and press OK, and it start now running it. All right, so we have here the input voltage, but let's go to the output voltage. I will see, yeah, it's going, it seems that it's stable, which is good, but the question is it because the PWM here is 50, has a 50% duty cycle, and we are assuming that the input is 50, so the output should be 50% of the input, which is 25 volt. But it seems that the voltage here is not a 25 volt, it's about 32, 33 volt. Why it's different? That seems it doesn't go with the relation that the V output equals delta, or the duty cycle, times the V input. And the case where we don't have this rule apply, where we have discontinuous conduction mode. I'm very interested to go and see the inductor current, and let's just click on it, and let's now zoom and see what is the inductor current here. Yeah, we know why now. It's discontinuous conduction mode, and in discontinuous conduction mode, V out doesn't equal delta V in. It has a different nonlinear relation. So we want to convert our converter now to work in continuous conduction mode, and we have different solution for that. We can increase the load current by maybe reducing the resistance, so the load current will increase, or we can really increase the inductance value. So if I increase the inductance value to 3 millihenry, for example, and run the system again, we'll see if that will drive it in continuous conduction mode or no. It seems now going above the 0 ampere here. Okay, that seems working. And now let's stop it and zoom in again. Yeah, it's now continuous conduction mode. What about the V output? Is it now 25 voltage? I think, yeah, it's 25 volt now. Okay, so that means V out equals duty cycle Vn, because now in continuous conduction mode, and it obeys to that rule. We can do the same if we return back this inductance to be 1 millihenry, but the inductance or the resistance, the output resistance, is about maybe 50 ohm. That means it will consume more current, and I think that will be sufficient to drive our inductor into continuous conduction mode. We'll see now if this will work or no. Yeah, it's still, I think, yeah, it's very close, very close. So it needs more current to be absorbed. Let's like 20, okay? And I think that will, yeah, that will drive it now to continuous conduction mode, okay? So again, what we are looking here is the transient, and we are not looking at the transient in the basics of power electronics. That's why we will look at just the steady state. What is the steady state? Here is the steady state. This is the current steady state. We have that value. We go up and down, and this is the current inductor current ripple. And we go to the voltage. I think we still have small ripple. Yeah, it is small ripple here, which is the delta V. We have equation for that, and we have equation for the ripple current as well. And because the voltage ripple here doesn't seem very smooth, so I can increase the simulation step size by going to this transient here and right click and go to the maximum time step to be, for example, 1 micro. 1 micro, that means every 1 micro it gets new data, okay? And I think let's run it again just to make it smoother a little bit, and we'll see the result. It might take longer a little bit, but I think the result will be very good. So let's now go to the, yeah, it seems now smoother, okay, and there is no piecewise linear relation here or lines, okay? So that's why it looks nice now. So now let's look at the switch current and also the diode current and compare it with the inductor current. We know that the on time, that part here, okay, is coming from the switch, and that part here is coming from the diode, okay, or going through the diode. So now let's draw the diode current, okay. Look at the diode current now. Let's just take one sample, okay. So the diode current here, which is the red one, it's the same as the inductor of current here, or of time. And look at the switch now, and that switch taking that current. So both of them now will combine or will form the current for the inductor. So you have to replicate all that just to make sure that you understand all the waveforms. You can go to also the capacitor current, and you will see the capacitor current is the ripple, just the ripple, which is the AC component of the inductor current, okay? And because in buck converter we have inductor here, so it will take the inductor current ripple, okay? So this will be exactly the same, and V output now, or I output, will go to the resistive load here, and it will be like a steady state here, okay? So that's why it's like a ripple and superimposed on the steady state going to the load, okay? And the capacitor just takes the ripple. So make sure that you know what is the reason for going to discontinuous mode or continuous mode. We change the inductance value, we change the load value just to make ourselves in the continuous conduction mode, and we make sure that the output value is the same as V out equal duty cycle times Vn. And this is the simplest test for buck converter. Now with the same circuit, I want to see the impact of the parasitic on the output signal. So maybe the capacitor parasitic has lots of impact. I can't actually simulate the saturation of the inductor, so I can't do it in LTSpice. So I will add now parasitic component for the capacitor, and we can add resistive first and then we follow it by inductive. So this is called ESR, equivalent series resistance, and I will choose it to be 500 milliohm, okay? And now let's run it and see the simulation result now. And what I want to see the current and voltage. Okay, so the output voltage now. Okay, let's stop it and see. Okay, now look at the shape we used in the first part to see like a sinusoidal wave here. Okay, exactly, maybe similar to sinusoidal, but we have here a shape like a triangular. And what is that similar to? I think it's similar to the inductor current. Okay, because the resistive component here mirrors the inductor current, because it brings the inductor current to the capacitor, the ripple one, and because the resistive load produces a voltage drop which equals IR. Okay, and I is the same as the inductor ripple current, and it's superimposed on the voltage output voltage here. So that's why we have this shape. Now if I reduce it more and more, for example 100 milliohm, even if it's in milliohm, but still affecting the shape. So now let's see the result. Yeah, it's going back now, but look at this part. Yeah, if you are looking to this part, yeah, it seems that, yeah, okay, we have still the impact of the resistive load here. Let's now add the inductive. I can add the inductive now by breaking this and moving that a little bit and adding an inductor here. And let's try first to make it, for example, 1 micro. Okay, it's high, but let's see the impact in the simulation. So it doesn't seem here anything. Okay, the resistive load here is still low, but let's see now what is happening. Okay, exactly, look what's happening here. So now that piece here happens because of the ESR. Okay, and that mirrors the inductor current, but that step happens because of the high inductance here, or high ESL, equivalent series inductance, and that might result from long leads for the capacitor or long tracks on the PCB. Okay, so this is the impact here of the ESL. So if I reduce that one to be 10 nano, for example, I think this will reduce a lot. Now it seems, yeah, it disappeared. Okay, so that's why this one is okay, and that's why we want the leads to be short. This is one of the consideration, and also it's very close to the other components and not long PCB tracks going between one component to another, just to reduce the inductance component and also the spikes that we have seen now, because also that will affect the EMI generation, and also it might fail your product. So that's it for the capacitor, output capacitor parasitic component, but we have parasitic as well for the inductance and for also the Mosfet, but what is impacting the output voltage is this one mostly. So that's why I give it more attention here. The next step is that Pwm generator here is practically doesn't exist like this, and it's just a signal generator, and maybe we got that PWM signal from microcontroller or from another device, but we want between our signal generator, PWM generator, and our Mosfet, we know we want a gate driver, and that gate driver is to speed up the switching and to make sure that the Mosfet is in saturation or cutoff very quickly, and that will reduce the switching losses and also will reduce the thermal stresses on our Mosfet. So in this part we are going to see what approaches we have to make a high side driver for this Mosfet. So the first thing we can think about is just to separate that generator. Okay, and we just move it somewhere. And that Mosfet needs high voltage to turn on and low voltage to turn off. So I will use a resistor, and that resistor is supplied by that supply. Okay, so the input supply will be also supplying the gate, and I will see if that's correct or no. Okay, This now will supply the gate and turn it on. But if I want to turn it off, I will use a transistor. So I will get another NPN transistor. So we'll go to NPN, and that NPN will come here. All right, and I also connect it like this and get a ground. And here we have another resistor. And we can connect it. That transistor can be 2N3904. Okay, very simple, straightforward. And now our generator can be connected to this point. We have the ground as well. And that resistor can be like 2.2 kilo. Okay. So I think we are applying now our signal, okay, to the gate, to the base of this transistor. And that transistor, once saturates, it will bring that node to ground. It turns off the transistor. So when I have a turn on here, it turns off the transistor. And when I leave it, okay, this will be cut off, and that node will be brought to the high side here by this source, okay, or by this resistor. That resistor might be like 4.7 kilo, okay, for example. Let's try it and see how it goes. So we have here simulation run. And now let's test what is the signal coming out from my generator here. Okay, and let's stop it. And what is the signal coming to our gate? But not just gate to source. This is what I want. Okay, so it looks okay. Let's now avoid looking at the transient and go just to the steady state and see what's happening. So the green one is our pulse generator, okay, and the other one, the purple one here, is from about, okay, it's like from 0 to 4 volt, and 0 to 4 volt is not enough to turn on completely my switch. It might turn it on, but it's not completely good for it, okay. So I might go to, again, reduce that one to 0.5 kilo, for example, and reduce that one to 2.2 kilo, for example, and run it again and see what is the result, and stop it. We have very high spikes here, okay. That spikes might be from the reverse recovery time of that diode, okay. But now let's look what's happening. So again, 0 to 4, 0 to 4, 0 to 4. We want to see the output if it's going right here. So let's now, okay, it seems that, yeah, it seems 20, okay, not 25. So that means we have here some voltage drop somewhere, which is about, it's maybe about around my, yeah, it seems around my Mosfet. Yeah, we have here voltage drop about 4 voltage, okay. So that's why it's not good to make that higher voltage drop across my transistor, because that voltage drop will be applied across the resistive RDS on. V squared divided by RDS on will produce high thermal stress. The different solution is to make a push-pull configuration, where we have here not just one transistor. We want to bring another transistor, which is NPN or PNP transistor. So let's go to PNP transistor, and that transistor will be, I think, yeah, 290 or 3905 or 06, yeah, okay. And let's arrange it in a way. And now I completed the push-pull configuration. We have the first transistor here, brings the current from the top here, okay, and go to the gate to charge it and turn it on once I turn it on, and that turns on when the PWM turns on or B1. So when the PWM is 0, so that turns on this transistor and that brings all the charge to ground and we turn it off. Okay, so let's now test this one and see if the output voltage will be alright and if the switching as well is right. So I'm expecting here the 50 volt there and 50% duty cycle, so the output should be 25%, 25 voltage, but I think it's 5 volt here, which is not really good. Okay, even if I lowered the output, okay, it doesn't seem going to 25 volt. Okay, that means the driving is not proper yet. Okay, so if I looked at the Pwm pulsation here, okay, and also let's now zoom out a little bit, and also the VGS between gate and source. Yeah, okay, look at that. Look at that. So from 0, maybe 1 volt to 3.5 or 4 volt, 1 to 4 volt, it's not enough to turn my MOSFET on. There is still a problem. I can't turn it on. This is the problem of high side switching. You have to use different topologies. That topology, it's very good for low side switching, but high side MOSFET driving, this is still lack of ability to turn it on. So one solution for that is called the Bootstrap. So the reason why this configuration can't drive that gate to be higher than the source by 10 or 20 volt is because it doesn't have it. Okay, so the voltage there, once this turns on, the voltage there will be close to that one. So from where you will get more voltage by 10 or 20 to be applied on the gate, and that's drive us to use something called Bootstrap Capacitor. What is Bootstrap Capacitor? So the Bootstrap idea is to have a capacitor like this, and that capacitor is referenced to the source. So I have that capacitor, and that capacitor now I will put it like that, and I will reference to the source. I will make one point here to be connected to the source. Okay, so the reference of that capacitor is the source, and if I charge it, I will build the voltage, but that voltage above the source. Okay, so I can take that voltage and give it to the gate by this configuration. Okay, so now instead of getting voltage from that node, okay, for this configuration, I will get voltage from that capacitor. Okay, so now if the capacitor is charged, for example, by 20 volt, okay, so that 20 volt will be above the source volt. If I take it and give it to this configuration here, it will drive the gate by 20 volt above the source. But there is one still small problem, which is how I charge it. Charging that capacitor will be by using the original source, which is the 50, and using that diode. Okay, so that diode now will charge it like that. Okay, so now if this node now is grounded, and that happens when this diode is on, so if the transistor now is off, during that time that node is very close to the ground because this will turn on. Okay, and that node is very low and that node is high, so it will push some current toward charging that capacitor. Okay, so now that MOSFET is off. During the off time, I have to make sure that my capacitor is fully charged, and when I want to turn it on, so that voltage now will be 50 volt because it has been charged by 50 volt. 50 volt more than the source voltage, and that 50 volt will go by this transistor now and apply it on the gate. 50 volt is more than what is needed, or more than the maximum voltage allowed to be applied between the gate and source. So that's why we have to make some protections, because we don't have here any problem driving that voltage, driving that gate by this voltage, so I will keep it. But practically, you have to insert some protection diode or Zeners between the gate and the source. So any higher voltage, it will be clipped. Okay. Now, if I choose in here 1 microfarad, I can't choose it very high because that will take longer time to be charged, and that will limit my high side driving. Okay. So, and that one will be maybe 1N4148. It's enough because it has just to deliver short time and also a small current. So this is how we use our Bootstrap Capacitor to drive our high side MOSFET using the push-pull configuration. So that push-pull configuration now will take the charge from that capacitor during the on time. So when this turns on, or the on time comes here, so that will turn on and bring the charge of that capacitor to the gate. Okay, and that capacitor now is already referenced to the source, so that charge of that capacitor or the voltage is already above the source voltage. Whatever the source voltage is, it will be above that. So now during the on time, that capacitor now will discharge and supply the charge to the capacitor to the gate to turn it on. But once this MOSFET turns off, if we turn on that MOSFET, that transistor here, we take all that charge to the ground. And once this MOSFET turns off, that capacitor now has time to recharge again. And that recharge comes by this diode. Now that diode will push some current toward that capacitor, and the current also will complete the cycle toward the ground by this diode. So that transistor here, we brought it here because we want to make everything reference to this voltage. Okay, so that voltage will supply the this configuration, and also supply the base once we turn off that one. Okay, so that one once turned on, it brings that point to the ground and turn off that point, and will turn off that MOSFET. That means the voltage comes here. So if I want to see the pulsation here, this is the pulsation here, and if I want to see the pulsation between the gate and source, it will be like this. Okay, so it's opposite to what we know. So this purple one is the source PWM source here, and the green one is the voltage between gate and source. And as you see here, 0 to 48 volt, which is very high, higher than the gate maximum value. That's why we have to make another protection here. Okay, I have inserted that resistor here, takes all the discharge current also through it if there is any discharge current, and also because it doesn't have in here the Miller effect. Okay, but it's very practical, it's very very important. So I just use here 3 milli instead of 1 milli inductor, because I want just to make sure that it's in the continuous conduction mode. Now let's try to run it again and look at the output. Okay, and we are expecting now 25 volt because now we have 50% duty cycle, and yeah, I think it's going to 25 volt. Now it's different from the first cases where we have 5 volt and different voltage, because we are not driving our MOSFET properly. Okay, so if your output is not the same as you expect, there are two reasons. Maybe you are going to discontinuous conduction mode, or you are not driving your MOSFET in a correct way. Okay, so this is now called the Bootstrap Capacitor. And there is another way to supply the proper pulsation for the high side MOSFET by not using high or Bootstrap Capacitor, because the Bootstrap Capacitor needs time to charge and recharge again, and that limits our speed. So what is the other option is to use another external source. I will use here another source like that, and that source here will be supplying my configuration, push-pull configuration here, and that's it. So this is another one. I can give it, for example, 20 volt here, and that's why we have to use another power supply for gate driver if I want to use another power supply, or if I don't want to use the Bootstrap configuration. So this is another solution, and I think this as well will be referenced as well to the, okay, we have to reference it to the source as well. So I can really remove all that and reference everything to the source. So that one, it's improper to reference it to the ground, because this will bring the problem again. So I will reference to the source again. So now all that circuit is between the source and the gate, and that voltage is between the source and the gate. So now if I want to run it, I will know if I'm driving it well or no by looking at the output. So now let's look at the output signal. Yeah, here's the output signal. Okay, and again it's going to 25. That means, yeah, we are driving our MOSFET in correct way. So if I now sense the voltage to source, I think we are going to get some pulsation. Okay, and that pulsation is from 0 to about 20, 0 to 20, which is proper one. So we have discussed how we drive properly the high side MOSFET. We started with improper driving, and then we use the Bootstrap Capacitor to drive push-pull configuration, and then we use an external power supply to do it. So in this part we will speak about the open loop and closed loop control of buck converter, but very briefly and in a simple way. So far we have built this buck converter, and we can control the duty cycle by this PWM signal, and the output voltage will change. So we have here 50% duty cycle, and I think the output will be going to the 25 volts. So let's now just wait, and I think, yeah, it's going there. Okay, and this is the transient here, and we are not actually going to set the transient. So the steady state will be going to 25 volt. That's good. Now if I want to change the volt, I can go to the duty cycle here and can change it, for example, to 70 micro. That means 70%, and I'm expecting here 70% of the 50. But look at what's happening here. We are not going to 70%, we are going to 14 or 15 volt, which is 30% of the 50. Why that happened? Because we have here an inverted PWM. Inverted PWM means the duty cycle is not the main controller here. Is 1 minus the duty cycle is the main controller, because we have the on time is reciprocated to off time, and off time is reciprocated to on time. So if I want to get 70%, I have to go to drive it by 30%. Okay, so the driver here is 1 minus delta, not delta. And that happens if you have inverted driver. We have inverted driver here. If we want to return it back, we can just add another transistor and we return it back to a normal driver. Look at that now. We have here 70% of the 50 volt, which is about 35 volt. Okay, and that happens 35 volt now, and yeah. So one thing to know, that we are now controlling our buck converter by duty cycle, by open loop, okay, and it's working. But if I want to add a feedback just to make sure that the output is accurate, or I want to supply different voltage later, so how I can implement the feedback loop? So now let's just close this one and maximize this one. So if we want to drive any system, we have to generate PWM here, okay? And that generator is considered as a programmable generator. But in LTSpice, I will replace that with a circuit, okay? So I will maybe remove this one, okay? And bring here a generator, and that generator is different from what we used to. PWM can be generated by using a comparator. And that comparator will compare a triangular wave with a voltage, maybe steady voltage, and that voltage will define for me the duty cycle. So I will show you what I mean here. So we will go to bring a comparator, and that comparator is from the op amp. Here we have op amp, and double click and you go to LT1213. So we will go to 1213, which is this one, 1213, this one, okay? So that one is a comparator. I will just mirror that, and mirroring that by Control E. Okay. And now we want supply. So from where get supply, I will mirror, or I will duplicate this voltage here and bring it there. And another will make a wire or ground like that, and wire. And then a net name, just to make sure that I want VCC. This will be supplying my just operation amplifier, and I will make VCC here as well, and will wire it. So that supply now is supplying my operation amplifier, and I will get a value of 5 volt, for example. Okay, so I will bring here a ground, and this is my supply for my comparator. Okay, and that will go to my resistor here to drive my driver, and also to my Mosfet. Now, I said that PWM generation can be implemented by comparing a triangular wave. Triangular wave, it has some circuits, but I will not do it by circuits, not to complicate my simulation here. So I will bring here another source like that, and that source is grounded. And I can generate PWM by this, but I want my duty cycle to be changed according to the feedback. So I will give here some values by advance to generate triangular wave. That triangular wave will finally generate for me the PWM. So I will get a value of 0, 5, and the delay is 0. The rise time, I want that the frequency of my switching is 10 kilohertz, so rise time will be 100 micro. The fault time will be 0, but I will give the value of 1 nano, for example. The on time will be also 0, because the ramp has no on time. It's just ramping to the maximum and then drop. And then the total period is 100 micro. So in that case, I'm rising by 100 micro during the 100 micro. Okay, so it will be like ramping, okay, or triangular wave. We will draw it now and see. Okay, now that source here, I can bring another source just to show to you what I mean. This is my source, and here is a ground. Okay, and let's now just wire it and see what I mean. Okay, now we have that comparator will compare that signal with a voltage. That voltage, I will choose it to be 2.5. Okay, 2.5 is a middle point between the 0 and 5. Okay, so there will be output on, off, on, off, on, off. Okay, that on and off, because this is a comparator, will be a result of comparing that 2.5 with the ramp signal. Okay, so I will assume, I will expect that 50% will be off and 50% will be on, because 2.5 is the middle in the compared with the ramp. Okay, and that will go to the circuit. Now let's run it and see if there is any problem. And now let's go to the output, and yeah, it takes now little bit of time, but yeah, it's going now to 25. It seems all right now. So there is some resonance or some oscillation here, and then 25 volt. Okay, so let's stop it, and yeah, approximately 25 volt. Okay, so that means here, if I want different duty cycle, I just change that voltage. For example, I will change it to 1 volt, and that one means 1 from 5. Okay, that means 1/5 of the duty cycle. Okay, which means approximately 20%. Okay, so I'm expecting it 20% duty cycle. Let's run the simulation again and see what is the value. So it oscillates about 10 volt, which is 1/5 of the 50%. Okay, and it's inverted one here, so that's why inverted and inverted, it will be proper one. So now this one means 10%, and 2.5 means 50%, and if I gone to 4 volt, 4 out of compared with 5, and this will generate about 80% of the voltage. That means I will go to maybe 40 volt. We'll see here where it's going. Yeah, the oscillation is higher here, but it's going to about 40 or 43, 42 volt. Okay, so now I have here a voltage that's controlling my duty cycle, and this is what I want. Okay, so let's now close this one and look at it again. Okay, so that's what that voltage, I don't want it to be the main controller, because that voltage is controlled by me. I want the feedback to control it, okay, or supply it. So that's why we will get another resistor. So how we get the feedback now? We can get a feedback by voltage divider from the output voltage. So here's the output voltage. I took it and feed it to a voltage divider, and that voltage divider now, for example, I will give it similar values. For example, 10 kilo and 10 kilo. So the value I'm expecting here, it will be halved here, okay? So that will be compared with my original value, okay? What my desired value. So again, we need a comparator, because we know that the feedback system goes to a comparator or summation and subtraction, okay? So I will implement here something called on-off control. On-off control means if my feedback tells me that I'm higher than my desired value, it will turn off the buck converter or the Mosfet. If it's lower, so it will turn it on, okay? So this is what's called on-off. So that's why I will duplicate my comparator here and take it there, okay? And I will bring feedback from there to the minus, okay? This is my feedback, and this is my desired voltage I want. Maybe I want from 0 to 50. I want, for example, let's make it a steady one. I want, for example, 20. Okay, let's see how it goes. Okay, so this is 20, and it will compare it and give us another value. So let's now see what is the result if I give it this value 2. So the result of my comparator here, or my subtraction, it's a comparator because it's on-off control, and that will drive my Pwm generation, and that will drive my Mosfet. So the maximum voltage here expected is 50, and I have to supply here from 0 to 5, to be honest, okay? So 50, if I want to supply to maximum as 5, so I have to divide it by 10. So that's why this should be 1 kilo. So that's why I made a mistake without setting these correctly. So now if this is 50, this will be 5, okay? Because this one is 0.1 division, okay? This is 5, and I have to compare it with from 0 to 5, and let's say 2 volt, okay? 2 volt here, it will be compared with 2 volt. 2 volt here means 20, okay? So every value I have here, it will be multiplied by 10 because I dropped it by 10, okay? So now let's try to run it again, because we learn from mistakes. Okay, what is the maximum value? Yeah, it seems very close to 20. Okay, so let's now stop it. Very close to 20. It's a 22, okay? There are some voltage drops maybe across my transistor, okay? Because I'm driving it by this way. Okay, maybe I can drive it harder by supplying higher voltage here. For example, 25 volt. Yeah, it might enhance it, but not that much, I believe. We'll see if there are some better results. No, it doesn't seem that. Still 22, okay? So now what is next? Now, this is called on-off control, and this is one of the simplest controllers. If I want to get, for example, here 30 volt, I just change it to 3. Okay? So that one is the user controller. So now it's about 30 volt, but it's not accurate, and it's still always giving some ripple, okay? And that ripple is not really sometimes it's small. Okay, if I change my load here, so for example it's not 50, it's 20. Okay, I think that the ripple now from top to bottom, it is about 2.3 volt in this bar here. It's 2.3 volt. Now if I want to run it with higher load here, it will be more ripple. Okay, yeah, it's damping but still more ripple. Okay, and oscillating for longer time, so it's still not very adequate for my control, and maybe I can enhance it. We can enhance it by providing some hysteresis. How we provide hysteresis? That means it doesn't turn on and off exactly at the same point, which is 3 here. Okay, no, it gives a margin. Okay, and that can be supplied or can be implemented using another resistor, feedback resistor. That feedback resistor comes from the output and also connected to the positive terminal, not the negative. Negative means negative feedback, and I can set it as 10K, maybe 10K to 200K. I will set it to 10K and see what's going. So this is hysteresis control, called, not on-off control. Yeah, it seems still the ripple continuous because it's still on-off but with a margin. Okay. Okay, now let's try to increase this to 200K, for example, and see if there is any good results. Okay, still the same. Okay, I have just one question. What about the inductor current? Because I have doubt about inductor current here. Is it continuous? It seems continuous conduction mode, so we have no problem with that because we have 3 milli here. Okay, so this is the on-off control and hysteresis control, and they are okay and easy to implement, but they are not really accurate, and that oscillation is continuous. It doesn't damp. Okay, so what do you think? What is next? I think we can implement, this is the last controller that I want to implement, P controller. Okay, how I implement P controller? I think we know P controller is a gain. Okay, and I can use my operation amplifier here to implement a gain. And I connect my resistor there and there. And I choose a random gain, for example. For example, here is 10K. I will choose a 10 kilo. And here is 1 kilo. So that means we have 10, gain as 10. So P controller and P is 10. Okay. So now let's run it again and see how it goes. Okay, this is the current here, but I don't want the current now. We'll see if the output is damping. Yeah, that's better now. The output is damping, the oscillation is damping and going to very small portion here. We still have 32 volt. I asked for 3 volt. Okay, 3 volt here. That means 30. Okay, so it seems that we need to make more enhancement, like PI control. I control reduce the steady state error to 0. Okay, but still I'm getting here small error, which is about 2 volt, between 30 and 30. But look at the result now. The oscillation is less. Okay, and here the damping is faster. Okay, within 15 or 15 milliseconds it finished. Okay, if I change my load to 50, for example, I think less load will make less oscillation. Okay, so now within 15 again it damps, maybe within 20. So now why not to increase the gain? So 10 kilo here, let's say 50K. So we have a gain of 50. Make sure that you don't destabilize it. And I think more gain will destabilize it. I think we are now, we have this destabilize it now. Why? Because more P controller can make it resonate all the time. Okay, that's why, or oscillate all the time. So that's why this is not proper gain. So let's now make it like 25K. We want good gain, but not oscillating. Okay, look at this, still oscillating for longer time. That's why we have to select maybe a lower gain. Why not 0.5? And you'll see now if I set this to 0.5K, that means that the gain is half, not 10, not 20. See if it will go to 30 and if it will damp the oscillation faster or no. So let's now see. Okay, that's good. It's damping. Okay, the oscillation. We are still within the 30 millisecond. Okay, it's good. Going to some value. It seems better than before because it's going not to 32. It's going to value here middle, which is about 30. We'll see now where it's going. We have 0.5 and 1 kilo. So the gain is lower, not higher, and that's good. Okay, now let's stop it and see the value there. 30, approximately 30. So maybe you can assume that okay, you want a little bit of eye controller here, and that makes it better. Okay, so if I want now to get different voltage, for example 20, I set this to 2 and it should go to 20. So I will see if there is a big steady state error, because PI control removes the steady state error, and I will leave it to you if you want to add PI control and how to use operation amplifier to implement PI control. It's going near to 20. I assume it will be 20 something, but let's see now. Okay. Yeah, 20.3. Okay, which is okay, good, acceptable, but implementing PI control makes it maybe steady state, maybe error less than this. Okay, there is a note here which is my output starts always from 50 and going to the desired value, and that's weird because I think the duty cycle is inverted, and maybe we can fix that by, I think we can insert another one here. Okay, that will make maybe the pulsation a little bit slower, but we can really take that one here. Okay, and another one like that. Okay, so it's another resistor, and this now wire them like this, and that's one. So I think this one will bring also another inversion. Let's now give this half kilo, and this one should be 2.2 kilo, something like this. We'll see how it goes. So the output now, yeah, it starts now from 0. Okay, so that's why the output sometimes comes from the 50, because the PWM is inverted. Now it looks better. See, the oscillation starts higher and then going down. So the starting point is not really important in transient, because the study is about the oscillation, about the damping. So starting point, wherever it is, it's not really a big deal, because sometimes the voltage changes from 50 to 20 and then to 30 and then to 40. So all that should expose similar transient. Okay, I think this is the what I want to tell you about the starting point for this transient. So I think that's it. I record this video by step and shared with you all the mistakes as well, just to make sure that you can re-simulate it or duplicate it again. Okay, so make sure that you can duplicate that work and you can enhance it for your coursework, and also you understand every bit and why we choosing that value and what's the expectation if we maybe change the topology. For example, if you change here this controller for different controller, what will happen? If you want to change the frequency, where is the frequency here that I can change to increase or decrease and see the effect on the ripple as well? Okay. I included also the driver for you, just to make sure that you understand all the system and how we design everything. So I didn't actually go for systematic design. I just want you to practice the simple design and without any calculation, how we are going to manipulate our values just to get a working converter, and then you can verify everything here by calculation. So I hope you are with me duplicating the work, and I hope you enjoyed implementing that work, because it's very good practice to know how the buck converter and how we drive the MOSFETs, and then how we implement a closed loop system. And then I will leave it to you if you want to make any advanced work. Thank you very much for listening, and see you in other coming videos.